with our second talk for today. And Joel Fan is going to tell us about new rational cubic fourfolds arising from Cremona transformations.
Okay, thanks so much. And thanks so much for the invitation to speak. All I'm talking about today is a joint work with Guowen Lai. So we studied some results on rationality of cubic fourfolds, and this has been mentioned several times in this workshop. But this talk will be more classical algebraic geometry, not much categorical things involved. I don't know whether you'll be more happy or not. So the outline is the following. So let me draw a picture. So say this is the moduli space of all the cubic fourfolds, and we're going to study a particular divisor. So later I'll define what this divisor is. So now let's denote this by C20. And so we define some a birational involution on this divisor. So, a birational involution. Let's call this F. So it will send a cubic fourfolds on this divisor to another cubic fourfold on this divisor, and these two cubic fourfolds will be birational. And that's the first thing. And the other thing is we can study the K3 category of the cubic fourfolds on this divisor, and the K3 category of the image under the birational involution. So one thing you can show is that the K3 categories are equivalent under this involution. And the other thing is there's no other cubic fourfolds have the same K3 category. So they're the unique pair of cubic fourfolds that have the same K3 category. And so the third thing is about some new rational cubic fourfolds. So this divisor, generically the cubic fourfolds here are not rational, but we can intersect this divisor with some other divisors where we know the cubic fourfolds are rational. So for instance, there are some divisors like C26 where we know the cubic fourfolds here are rational. So we can look at the intersections. So the intersection will have several components. So these are codimension 2 in the whole moduli space. And then applying this involution, we'll get so map to F. And so these will be some codimension 2 components, and we can show that there are some components where the image is not in the locus where we previously know our rational cubic fourfolds. So there are some new kind of rational cubic fourfolds. That's the third part. So this is the picture of what we're going to see. So one interesting question for mirror symmetry is that what's the mirror of this involution F? So there's a result by Sheridan and Smith that relate the K3 category with the Foucault category, some K3 surface. So it'll be interesting to see what's the symplectic analog of this involution. So this is supposed to be an involution on some codimension 1 locus of the symplectic structure of the mirror K3. Okay. So I'm going to recall some backgrounds on cubic fourfolds and then state the results more precisely. Okay. So let me first just recall some Hall structures on cubic fourfolds. So in this talk, X is always a cubic fourfold, a smooth cubic fourfold over C. And we let this curly C to be the moduli space of cubic fourfolds. then you can compute the dimension. The dimension is 20. And the Hodge diamond of a cubic fourfold, Hodge diamond, the only non-trivial part is the middle cohomology, and the middle cohomology has the middle one has 0, 1, 21, 1, 0. And so there's a Taurida theorem by Bolzan that the Hodge structure determines the isomorphism classes of cubic fourfolds. And so we can compare these numbers with the Hodge numbers of K3 surface. And so if you can, let's say this is a K3 surface S. So the middle cohomology of K3 surface is 1, 20, and 1. And the signature is 3, 19. So if we want to relate these two, then so the signature of this is 21 and 2. Maybe I should. And then we take the primitive part of both cubic fourfolds and the K3 surface. So if you look at the primitive part, then there will be 0, 1, 20, 1, and 0. And it has signature 20 and 2. So they have the same Hodge numbers, but the signatures are different. So if you cut down one more dimensions, the primitive S is 1, 19, 1, and the signature is 19 and 1, 2. So the reason that we want to relate the Hodge numbers of H4 with some middle cohomology of a surface is that if we expect the fourfold to be rational, then we know there's a weak factorization theorem that every birational map can be decomposed into blow-ups and blow-downs. And if you blow up a fourfold along a surface, then the blown-out surface, if you look at the middle cohomology, it will be the sum of the middle cohomology of the original fourfold plus the middle cohomology of the surface that's blown up. So if X is birational to P4, then we'll hope that these numbers are coming from some cohomology of a surface. So now if we compare these two, now if we cut down one more dimension in H2 too, then they will have the same signature. Then we can hope that they may be the same. So that's a definition to define. So we say a cubic fourfold is special if there exists some algebraic class H22 such that it is not homologous to a square of the hyperplane class. Okay. So this is at least rank 2. And we define the discriminant of H2 and T to be the determinant of the intersection matrix H2, H2, H2T, H2T, and T squared. And so another definition. So we can collect all the special cubic fourfolds with the same discriminant and denote this by CD. So these are special cubic fourfolds with T such that the discriminant equals to T. Okay. Right. And now we can ask what kind of special cubic fourfolds. If we look at the orthogonal of H2 and T, it would like really be isometry to some primitive part of the H2 of some K3 surface. And so that was done by Hassett. So theory. Yeah, so first of all, like this CD is non-empty, so the discriminant can appear for some D. If only if D is bigger than or equals to 8, and D is 0 or 2 modulo 6. Okay. So this kind of D can appear as some discriminant of H2 and some other algebra class T. And furthermore, so suppose there exists some H2T such that the discriminant is D, then like that there exists a polarized K3 S such that, I should continue here, such that the perp of H2 and T, so the perp we take in H4 is isometry to the primitive part of some K3 surface, which by negative 1. If and only if D is not divisible by like 4, 9, or any odd prime modulo 2 equals to 2 modulo 3. So it turns out that the condition of like the perp of this is isometry to some primitive part of polarized K3 is determined by just this the number D. Okay. So for this D, there's such like associated K3 to the cubic fourfolds. And so the first few examples of D are like 14, 26, 38, 42, 62, and so on. Okay. And the conjecture by Hassett is that a cubic fourfold is rational if and only if there's such associated K3. Okay. So a cubic fourfold is rational if and only if there is such associated K3. So in other words, like the fourfold is in these divisors. And the remark is that the conjecture is true for like all known examples. So the examples that we can, that there's a proof that the cubic fourfolds are rational are like the first 4 examples, like C14, C26, C38, C42. So these are by Rousseau. That but for like other D's, we don't know like whether they're rational or not. But conjecturally, like for these D, the cubic fourfold should be rational. Okay. Questions? So I was like say a few words about the derived categories. So so we know that the cubic fourfolds has a semi-orthogonal decomposition, AX 01, 02, and it's proved by Kuznetsov that this is a K3 category. So, like AX is a K3 category. namely the Serre functor is shifted by 2. And it's conjectured by Kuznetsov that the X is rational if only if the AX is the derived category of some K3 surface. It is a geometric K3 category. The X is rational if only if AX is equivalent to some S for some K3 surface S. So it's a geometric category. And so the natural question is whether these two conjectures are equivalent, and that was proved by Addington and Thomas in the generic case, and like more recently by Bayer, McCree, Newer, Harry, Starry. So there's a very long paper by them. So these two conditions are equivalent. So X has kind of Hodge theoretic K3, theoretic associated K3, if only if the K3 category is equivalent to some direct category of some K3 surface. So these two conjectures are equivalent. Okay. And so another kind of related conjecture, so related to like how this K3 category determines the directional geometry of the cubic fourfold is the following conjecture. So if two cubic fourfolds, X and X prime, have the same K3 category, such that AX is equivalent to X prime, then X and X prime are birational to each other. They are birational. Okay, so now I can state the main results. So theory. So we show this conjecture in the special case, like for the fourfolds lies in that divisor C20. So the conjecture holds if X is like generic cubic fourfold in C20. So maybe I should write it more precisely. So it's a generic cubic fourfold containing a Veronese surface. Okay, containing a Veronese surface. That's equivalent to it's in the C20. And so another result is like these new rational cubic fourfolds. So we find new family of rational cubic fourfolds in C20 intersect C146, 182, and 314. And then you can check that these numbers satisfy the condition. So it's in this Hass's list. Yeah, so conjecturally the whole divisor, like C146, 182, and 314 will be all rational. But like using this method we can prove at least like this codimension 2 part is rational. Okay. Questions? Okay, so these are some backgrounds on fourfolds. And now I can talk about the main technique, which is the Cremona transformations. So Cremona transformation on P5 via very easy surface. Okay. So let's very quickly recall what is a very easy surface. Okay. So it's what we see in the classical algebraic geometry. So the surface in P5 is called a very easy surface if up to projective equivalence it is the image of P2 under the Veronese embedding. Under this embedding. So we send a point in P2 xyz to x squared xy, y squared yz, z squared xz. So all the quadratic monomials in xyz. And we can try to write down what's the defining equation of v. So we let this x0 through x5 to be the homogeneous coordinates of P5. Then you can see that the 2 by 2 minors and the 2 by 2 minors of the matrix x0, x1, x5, x1, x2, x5, x3, x3, x4 are a defining equation of the Veronese surface. Okay, so you can easily check this. Anyway, so these are some quadratic polynomials in P5. Okay. So we can use these quadratic polynomials to define a directional map from P5 to P5. Okay. So let's say the defining polynomials are Q0 through Q5. Then we could define where's this? Okay, so we define a directional map from P5 by Q0 through Q5. So we use these 6 quadratic polynomials to define the map. And because these are defining equation of V, so V will be the base locus of this directional map. So some fact, so F is birational, and the base locus is V. And the inverse, so another fact is that the inverse, the base locus of inverse is also a Veronese surface. Okay, so this base locus of F inverse is also a Veronese surface. Okay, so let me denote this by P5 prime. Okay, so now we're going to look at cubic fourfolds that contains the Veronese surface. So cubic fourfolds containing a Veronese surface. Yeah, and later we'll see that such cubic fourfolds, if we look at the image, then the image will also be a cubic fourfold containing the Veronese surface on P5 prime. Okay. So some fact. Right. So if you compute the intersection matrix of the h squared, hyperplane squared, and the Veronese surface V. So you can compute the intersection numbers. There are 3, 4, and 12. So the discriminant would be 20. Okay, so discriminant of H2 and V is 20. So in particular, it is not in Hass's list because like 4 divides 20, 5 also divides 20. So we don't expect, so there's no associated K3 surface, and we don't expect like a generic elements rational on this divisor. Okay, so not in Hass's list. So the geometry looks like the following. So we have a Veronese surface in P5, and there's a Cremona transformation, a directional map on P5, P5 prime, and there's another Veronese surface which is a base locus of the inverse, and there's a common blow-up of these two. So like, let's call this P, it's G and G prime. So G is the blow up of P5 along V, and it's also isomorphic to the blow up of V prime, P5 prime along V prime. And so now we want to look at the cubic fourfolds that contains the Veronese surface. So it's in P5 contains V. And then we can look at the strict transform of X onto P. And let's call this Y. Okay. So that's a blow up of X along V. Okay. So we have some fourfold also in P. Okay. And the proposition we're going to prove is let's call this F. So the map, like sending X to this image in P5 prime, gives a birational involution on C20. So in particular, we want to show that the image Fx is also a cubic fourfold and contains V prime. Okay. So we want to show that Fx is a cubic and contains V prime. Okay. So let me sketch the proof. So we let L to be the pullback of O1 on P5 through G. So L is a element in the Picard group of P, and let M to be the pullback of O1 on P5 prime, and we let E and F to be the exceptional classes of the blow-ups G and G prime, classes of G and G prime. Okay. So now, so let's look at some relations between these classes. And so these are all in Picard of P. So because like F is defined by some quadratic polynomials, so because F is defined by quadratics, so we have M is equals to 2L minus E. Okay. And similarly, like we have L is 2M minus F. Okay. Because the inverse is also defined by some quadratic polynomials. Okay. And now if we look at what's the corresponding class, the class correspond to Y. So because X is a cubic, so like this blob Y will have, so Y corresponds to the class 3L minus E. 3L minus E. Okay. So the fact that fx is cubic and then v prime just follows from like a very nice symmetry. So we have 3O minus E equals to like L plus M, and this equals to 3M minus F. Okay. So it happens that if X is cubic, then this argument shows that the image is also cubic. So in this way, you can get an involution on this divisor containing invariancy surface. And so now we want to prove the following results. So for X generic, fx is not isomorphic to X. And AX and AX prime with fx. So maybe denote this by x prime, which is fx. So they have the same K3 category. And finally, x prime is the unique, is fx. It's a unique cubic fourfolds satisfying the condition that the K3 category is equivalent to the K3 category of X, okay. So except X itself. So the first statement is that this involution is a non-trivial involution for generic elements in the divisor. And then they have the same K3 category. And like, moreover, the image fx is a unique cubic fourfolds that share the same K3 category. So in this case, like, we can show like the conjecture. So this in particular implies that if AX is like equivalent to AX prime, then and like X is in C20 generic, then X and X prime are birational. So that's like the conjecture stated in the beginning. So in this particular case, we can like directly construct what's the corresponding X prime by the Cremona transformation. Okay. So what's the time? 05. 03. Yes.
Just to get a sense of what's going on, how large is the subgroup of birational automorphisms of P5 of those that preserve C20? Like, does it contain, for example, elements of infinite order?
How large is the?
Like, I'm just wondering, you're working with this involution, but like, what if I take any other rational transformation of P5 that preserves? Yeah, but the preserves cubic fourfold in C20 that sends it to another.
Yeah, you know, it's like. So it may not may not send cubic to cubic, I guess.
Ah, okay.
Yeah.
Sorry.
Yeah, but yeah, we can. So then now I'm going to like sketch the proof of these statements. Okay, so sketch. So the first part. Okay, so we have this diagram like x in P5, P5 prime, x prime, and okay, there's y. Okay. So y is the blow up of x along v and a blow of x prime along v prime, and we can use blow up formula to compute the algebraic lattice and transcendental lattice of. So you can use blow up formula to relate the algebraic and transcendental lattice between x and y, and also y and x prime. So the blow up formula implies that the transcendental lattice of x is canonically there's a canonical isometry to Ty, and there's another canonical isometry to Tx prime. So these are the transcendental lattice. So it's the orthogonal of the algebraic lattice that occur in H4. And so this is some explicit like transformation. And if you look at what happens on the discriminant group of these lattice, so that's dtx. So these are the discriminant groups of the lattice Tx. Then you can compute that these two groups are both cyclic group C20. And the map is given by multiplication by 9. So this is going. So this will implies that x and fx are not isomorphic, because if x and x prime are isomorphic, then we know that two cubic fourfolds are isomorphic if only if like they're projectively equivalent, and so x prime are projectively equivalent, and this implies that it will send the hyperplane class to hyperplane class and Veronese to Veronese. So the action on the the action on the discriminant group should be trivial. So this implies the action, the induced isometry Tx to Tx prime is trivial, and this contradicts with this computation. Okay. So that's the first part, and so for the second part, we're going to use a result by Weber's, the theorem by Weber's. So it's like a kind of derived Torelli in this case. So for any D and for any generic element in CD, the K3 category, the AX is equivalent to some AX prime, if only if there's a so for this K3 category, you can associate certain Mukai lattice, and this is equivalent to AX prime C Hodge. Yeah, so as in algebraic as in like abstract lattice, it is just the same as the Mukai lattice of K3 surface. So if we want to show like the K3 categories are equivalent, then it is equivalent to showing that these Mukai lattice is equivalent. And by the first part, we have the transcendental lattices are equivalent. And then, so we have this Tx is equivalent to Tx prime. And there's an embedding from the transcendental lattice to Ax, Z. And there's embedding from here to Ax prime Z. And so let's call this lambda 1 and lambda 2. So we think of lambda 1 and lambda 2 are abstract lattices. And there's result by Nicolin that so he proved that under certain cases, the embedding from lambda 1 to lambda 2 is unique up to automorphism from lambda 2. So his result can be applied in this case. So the embedding lambda 1 into lambda 2 is unique up to isometries on lambda 2. So there's a we can think of there are two embeddings from this Tx to here, and then you go through here and then go to lambda 2. So if there is a unique, if the embedding is unique up to automorphism lambda 2, then this implies this isometry can be extended to the Mukai lattices. And by Hoiberg's result, this implies that the K3 categories are equivalent. Okay. So here we use, so the main tool is the extension result by the cooling. And so for the third part, we need to, so basically we need to compute the numbers of cubic fourfolds sharing the same K3 category. And that's similar to a computation of Fourier Mackay partners on K3. So given a K3 surface and how many isomorphic classes of K3 surface share the same derived category. So the third part is very similar to Hosono's computation of the number of Fourier Mackay partners of K3 surface of so the counting would be equivalent to count the number of certain over lattices, count the number of certain Hodge isometry classes lump L such that L is an over lattice of certain lattice S and T. So here S is the algebraic lattice intersect with the primitive part. So it is just a rank 1 lattice in this case. Okay, rank 1. And T is the transcendental lattice of X. So basically this reduced to contain certain isometry classes that satisfy that is the over lattice of the sum of these two. And so basically we follow the proof of Hosono So it turns out that the number of the Fourier-Mackay partner of AX is equal to 2. So there's, except for X, there's a unique X prime that shares the same K3 category. So this proves the third part. Okay.
So do you need generic condition for these three?
Yes, yes. Yes, we need that. Good. So if it is not generic, then like S would be some higher rank thing. The computation will be different. Yeah.
Can I ask you why the discriminant, getting discriminant lattices multiplied by 9? Is there some explanation?
No, it's by like explicit computations. There's some, yeah, we have to compute some 3x3 matrices. Yeah. Okay. So. Okay, so the last part of my talk is some new rational cubic fourfolds. New rational cubic fourfolds. Okay. So the idea is that now we have this involution on C20. And then we look at the intersection of C20 with the divisors where we know the fourfolds are rational. So for example, we consider C20 intersect C26. So we know that these are rational cubic fourfolds. And so first, we need to show that there exists an irreducible component of C20 intersect C26 such that let's call this D, such that for a generic element in this irreducible component, the algebraic lattice looks like so it is spanned by H2V and another class T. Okay. So T has discriminant 26. And H2VT. So the intersection matrix looks like the following: 12, 5, 5, 14. Okay. So if you check, like the discriminant of H2 and T would be 26, and for different irreducible components, like this number will be different. So we choose we start with some particular component, and then use the blow-up formula to compute what's the intersection matrix of the image on the Cremona transformation. So and by blow-up formula, can compute the image. Let's go. The image is x prime, and it is spanned by h prime squared v prime t prime, where the intersection parent matrix is like 3, 4, 7, 4, 12, 7, -7, -7, 65. Anyway, so there's explicit computation. And then you can check that the discriminant between H2 prime, T prime, would be 146, and this is in like in Hass's list. So satisfy those numerical conditions. And another thing, so one can check that X prime does not lie in C14 or C26 or C38 and C42. Okay. So you can check that if you choose any class in the algebraic lattice, then the discriminant with H prime squared will not be these 4 numbers. Okay. So this is so this produces a codimension 2 components of like new rational cubic fourfolds. Okay. So maybe one final remark. Right. So there's some interesting happen. Like so, if we look at this device of C20, and for instance we look at the intersection of this with like C14. So there are like around 9 components, but under Cremona transformation, like some of them maps to maps to again the same component, but some of them will maps to discriminant C26, C38, C62. So like the image under Cremona transformation of these intersections in general will send to like different discriminant. So yeah, there is some interesting thing going on under for these codimension 2 or higher things. Okay, so I'll stop here. Thank you.
Thank you. Questions?